All right, all right, all right. Let's get back to work, students. We're going to start the other indeterminate forms of L'Hopital's rules. There was a few more. If we go back up to the table real quick, I'll look at it real quick. We just got done doing those two. In this video, we're going to do these two, and then in the next video, we'll do the versions that have exponents. Okay? Let's get back down to where we were. So this is another thing that has a L'Hopital's rule, and we're gonna have to show that it is L'Hopital applicable. L'Hopital is definitely doing a function over another function. Okay, so we'll see that we can rewrite these, which is what we're doing in this video. We'll see that we're able to rewrite those in a form that L'Hopital works. Okay. Let's just do the limit as x goes to 0 plus, or from the positive side, 1/2 x times the natural log of x. This is 0 times infinity. The way we go about it is x is the same thing as 1 over 1 over x, which is confusing as fuck, but it's true. You'll notice if I multiply top and bottom by x, the top is x, the bottom is 1. And we just end up with x. Another way of looking at this is multiplying this by 1 over x by 1 over x. And when you do that, you get 1 on top and 1 over x on bottom. Okay? So what we need to do is rewrite it in a L'Hopital version form doing this. Rewriting it as that. Okay? I'm going to move the x to the bottom as 1 over x. I could have moved the 1/2 or the 2 down there, but it would have confused. It's easier to confuse stuff. I did it this way. Now when we do plug in 0, natural log of 0 or something going to 0 from the positive side is infinity. And 1 over 0 from the positive side is also infinity. So this is L'Hopital applicable. So we're going to show that we're doing L'Hopital's. We're going to use L'Hopital's rule. When you do, you get 1 over 2x on top. You get negative 1x squared on bottom. Sorry, 1 over x squared, not negative x squared. And then we're going to clear fractions. This will just give me a negative 1 on bottom. This will just give me like an x over 2 on top. This cleans up to negative x over 2. And now when I apply 0, I get 0. So the derivative of this is 0. It's kind of neat. And other than that, we wouldn't have had it, like, this would have been hard to figure out. You would have had to get out a calculator and start checking values. Okay? What about limit as x goes to 0 of x times tangent x plus pi over 2? When we go to 0, x goes to 0. When x goes to 0 for tangent of x plus pi over 2, we're going to tangent of pi over 2. If you remember your graph for tangent, that is going towards infinity. So we have 0 to infinity, or 0 times infinity. We're going to rewrite this by moving the x to the bottom as a 1 over x. And now when we do the limit as x goes to 0, we get infinity on top and bottom. When that happens, we now have a L'Hopital applicable form. We can take the derivative of top and bottom separately. The derivative of the top is secant squared, x plus pi over 2. Then you take the derivative of the inside, but the derivative of the inside is just 1, so it doesn't change it. The derivative of the bottom is negative 1 over x squared. I went and moved secant down to the bottom as cosine, and I rewrote this as x squared on top, as we're allowed to do. This is still 0 over 0. It's another L'Hopital form. So we're going to do L'Hopital's event again. We take the derivative of the top, we get negative 2x. Take the derivative of the bottom. This is a chain rule. We get negative 2 cosine of x plus pi over 2 sine of x plus pi over 2. Remember me talking about the 2 sine or sine 2x form earlier? That's what I did here. I rewrote this here. But note that this negative cancels that negative. And then I did that, go into that. All right. Another L'Hopital event. Take the derivative of the top. Now we've just got, why do I have a -2? I shouldn't have a -2. Look at that. Because I cleaned it up. I just got 2. The derivative of the bottom, the derivative of sine is cosine. The derivative of the inside is 2, so I've got 2 cosine 2x. That should be a positive. That should be a positive. When we stick in 0 on the bottom, we're getting cosine of pi, which is -1, which is going to give us a limit of -1. Okay? So, a lot of stuff going on here. Gotta go patient, gotta be slow, gotta make sure you do it right. Let's take a limit as x goes to 0 from the positive side of 1 over x minus 1 over sine x. We get 1 over 0 minus 1 over 0, which is infinity minus infinity. This is another indeterminate form. You might be inclined to say this equals 0, but it doesn't. Sometimes it does, but it usually doesn't. As we'll see when we do the final video, the end of the video, we'll compare growth rates of things. We'll see some things go to infinity faster than others, so the combined limit doesn't necessarily mean 0. So we're going to rewrite it by getting a common denominator. I'm going to multiply this, put that there. I'm going to multiply this, and I get sine x minus x on top. The denominator for both is x sine x. Now when I plug in 0, I get 0 minus 0 over 0 times 0, and we get 0 over 0. That is L'Hopital applicable. So we do a L'Hopital event. Make sure you show me that you're doing L'Hopital. Derivative of sine is cosine. Derivative of x is 1. This is a product rule on bottom, x sine x. You've got to do the product rule. When I took the derivative of this, I got another 0 over 0, which meant another L'Hopital. The derivative of the top is now negative sine x. The derivative of the bottom, this is just cosine x. This is another product rule. So you got to do the product rule again. And I had plus cosine x and then minus x sine x. Now when I stick in 0, this is 0, this is 0, but these are not. So we get -0 over 1 plus 1 minus 0, and -0 over 2 is 0, which means this limit up here equals 0. Which was what you might have wanted to say with infinity minus infinity anyways, but you can't make that assumption. Okay? Let's take a look at 1 over cosine of x minus pi over 2 minus 1 over x squared. We're going to do limit as x goes to 0 from the positive side again. This gets us infinity minus infinity. We're not going to assume it equals 0. We're going to go through and get a common denominator. So I move the multiply to get an x squared up there. I multiply the right one by cosine of x minus pi over 2 to get that up there. And I get x squared minus cosine of x minus pi over 2 over x squared cosine of x minus pi over 2. Again, L'Hopital applicable. That's what we wanted to show. Now we can use L'Hopital's rule. So we'll take the derivative of the top and bottom separately. X squared goes to 2x. Negative cosine goes to sine. The derivative of the inside is just 1, so the chain rule doesn't fuck it up. The derivative of the bottom is a product rule. So I did derivative of this first, and I got my 2x cosine. And then I did the derivative of cosine, leaving x squared alone. Derivative of cosine is sine, negative sine. So we ended up getting that. So when we stick in 0 here, that goes to 0, this goes to 0, this goes to 0. But that does not go to 0. Sine of negative pi over 2 is -1. So when we clean this all up, we get -1 over infinity, which means it's going to a negative infinity. That's deep. Deep! God, I hope that's going to the right sign. I might have to look at that on Desmos in a second. Because if the bottom happens to be doing... No, they're both doing 0. 0 minus 0 is 0. I'm just going to leave that alone for now. We'll do another video. I'll see y'all in a second. I hope you guys are having fun. Peace.